Jai Hind all of you once again. So I am in front of you, Manish Kumar, Assistant Professor in Department of Computer Science and Engineering at Kumar Garg Engineering College. So today I am going to brief about another important topic of unit number 4, that is computational learning theory. Several times this question has been asked in university examination ki what is computational theory, how we can elaborate the concept of computational theory, how it is related to machine learning. What we are going to do in this topic, let us see. So, as the name suggests, computational learning theory, we have already studied that a machine learning is a multidisciplinary subject. So, in machine learning, what we will do, we will just give a number of examples, number of instances to a machine, and the machine will behave accordingly. It will give the output, it will give the result according to the algorithm that we have implemented, that we are going to implement. Okay. So, in computational theory, the challenge comes here that we will see a lot of complications in implementation of those learning algorithms. So, here in this topic, we will see that some theoretical implications that we will see in the implementation of learning algorithms, machine learning algorithms, and capabilities also of the machine learning algorithms under this topic. So, let us start computational learning theory. So, there are a lot of questions that arises in our mind ki what are the different possibility to identify the classes of learning problems that are inherently difficult or easy or independent of the learning algorithm. These are the questions. This is the first question that arises in our mind. What are the capabilities? Means we have instances, lot of instances saying whether this can be implemented or not, yes or no. So, if a new instance came, then where we have to put that instance, in what class, according to the given example. Secondly, a question arises, can we categorize the number of training examples, ki how many training examples are necessary or sufficient to assure successful learning? Is there any that counting ki how many training examples we need? This is again a question for us. Also, how is the number of examples affected? Affected means if observing a random sample of training data, can we observe that? Secondly, if the learner is allowed to pose the queries to the training example, can learner give the queries to the queries to the trainer? Several examples. Another, can one categorize the number of mistakes that a learner will make before learning the target function? Because we know that firstly what we will do, the main concept here is that we will just devise a target function, then we will approximate it. So, can anyone categorize how many mistakes that mistakes will be done by the learner that will before explaining that target function? This is another question. Next, can one categorize the inherent computational complexity of a class of learning algorithm? Can anyone define it? So, these are the some questions that came in our mind while doing the implementation, while implementing any algorithm in machine learning. So, importantly, firstly, the question arises what will be the size of the data set? How big is that data set? So that we can summarize that my machine will generate efficient outputs. So, these are the questions. So, all these questions will be answered using this computational learning theory. Okay. So, computational learning theory is very relatively recent field. It is very intense area of research. Partial answers to some questions that I have just previously defined can be given. So, we have to just elaborate those questions, see how we can find the answers. So, we will generally focus on certain types of learning. So, one learning is computational learning theory that we are going to focus here. Okay. So what we are given? We are given with hypothesis space, as we have already discussed, hypothesis space H, right, and the number of instances that is provided. Those instances were defined for any particular hypothesis. So we have earlier defined that hypothesis that I am considering, that H must belong to my hypothesis space, that we have already defined. So this hypothesis space will be given for the implementation of that algorithm in machine learning. Secondly, training examples are given. So the question arises that how many training examples should be given to that machine so that it can provide efficient output, right? So what we want to know, how many training examples are sufficient to successfully learn the target function. This is the main question that we are going to answer here. Secondly, how many mistakes a learner will done before succeeding, before getting the output, how many mistakes are done by the learner. So these are the things that we want to know. These are the given, hypothesis space is given, training examples are given, and what theory we will implement to find out that efficient solution. Okay. So computational learning theory provides a theoretical analysis of learning. So thus keep in mind, it will provide a theoretical analysis. As I have said before, theoretical analysis means it will provide the difficulty of several types of machine learning problems, difficulties as well as capabilities, okay, of those machine learning algorithms. So what are the solutions? We are just going to find out can you identify the classes of learning problems that are inherently difficult or maybe easy? Number one. Can we categorize the computational complexity? Computational means we are going to do some computation. Complexity means we are just going to find out the complexity of the classes of the learning problem. Okay. So when a learning algorithm can be expected to succeed, or when learning may be impossible, it may be a case. Okay. Next, can we categorize the number of training examples that are necessary or sufficient for successful learning, so that after studying this computational learning theory, we will summarize, we will find out how many training examples are sufficient for the successful learning. So these are the questions that come in our mind while implementing the machine learning algorithm. So this, with the help of this computational learning theory, we will answer all these questions. Okay. Several times number of questions arises in our mind, right? These are the questions that come in our mind. So how is this number affected if we allow the learner to ask questions? That is called active learning. How many mistakes will the learner make before learning the target function? So whenever we are going to study about this computational learning theory, these questions arises. So this computational learning theory gives the answers of these questions. Okay, the class of learning problem, computational complexity of the class, where it will lie, number of training samples, how many mistakes will learner make before learning the target function. Okay. So what we have to do, we just have to keep in mind some attributes, okay, that I have written here. Quantitative bounds can be set depending on the following attributes. So first of all, number one is, first attribute is the accuracy to which the target must be approximated, because in each learning algorithm, machine learning algorithm, after finding the target function, we will just use to approximate the target function, because according to the target function, some target output is there, and it is not always possible to get the correct output. There may be some error. So obviously we need to approximate it. We need to implement some type of rule to approximate it. Okay. Second attribute is the probability that the learner will output a successful hypothesis, that probability. Okay. Third attribute is the size or the complexity of the hypothesis space. That is always the matter of consideration here, that hypothesis space H. Okay. The manner in which training examples are presented, this is also important. Okay. We have also studied several examples. For example, whether my friend is going to enjoy his favorite sport on Sunday morning or not. So there are several climatic conditions also, wind is blowing or not, temperature is hot or cold. Okay, it may rain or not. So there are several attributes on the basis of which we can decide whether my friend will play his favorite sport on the Saturday morning or not. हाँ, this is the training example. ठीक है, so the training examples are presented to the learner. In what manner they are presented? So depending on these, we will decide ki whether that machine learning algorithm will output efficiently. Okay, so these are the attributes. So the computational learning theory will generally concentrate on the three general areas. Number one, the sample complexity. Number one is the sample complexity. Sample complexity means how many examples we need to find a good hypothesis. So this is important. This is important. Sample complexity. Okay. Number two is it will focus on the computational complexity. How many computational power we need to find a good hypothesis. Always here. Good hypothesis. Number one, need to find good hypothesis. Number two, need to find good hypothesis. Number three, also need to find good hypothesis. And the third area is mistake bound. So how many mistakes we will make before finding a good hypothesis. So we just concentrating on the hypothesis, because we know that we are just going to consider a hypothesis H that will belong to some hypothesis space, because I have already defined that hypothesis space is defined as all the legal moves, and out of those legal moves our best move is going to come out. Okay, so this H will consist of all the legal moves, and all legal moves were in that space, hypothesis space, and we have to find out a one best move. Okay, in the example that we have discussed before in checkers or in chess playing problem. Okay, so there are three general areas, so always keep in mind, this is important when the question asks about computational learning theory. Number one is sample complexity, number two is computational complexity, number three is mistake bound. Okay, so there are how many training examples is sufficient to learn target concept? This is the one important question that is always in our mind while implementing the machine learning algorithm here. So scenario one is that what is active learning? Active learning means I am fully active, teacher is fully active, है ना? So learner proposes an instance. Learner will propose an instance as queries to teacher. मतलब he will ask the questions. So question means he is asking the query. He or she will asking the query. Learner will asking the queries to the teacher. So query is that learner will give a instance, number of instances, and the answer is teacher. And teacher will give some concept. This Cx. This we have already studied before. This Cx is termed as a Boolean valued concept. We have studied Boolean valued concept. Okay. So this is a first scenario of active learning. First scenario of active learning. Okay. In second scenario, passive learning from teacher. Teacher will give some example, selected example. So teacher who knows C, teacher knows how I am going to implement the concept. Okay. So teacher will provide the training example here. Then sequence of examples given by the teacher that is defined as a set xi, comma cx. On the basis of that concept, it is defined as a set. Okay, that sequence of examples. Okay, first example, second example, third example. So we have defined using this variable I. Okay, and teacher may or may not be helpful here. May or may not be helpful in this passive learning. Okay, if a student is interested, then he can ask to a teacher. Otherwise, he or she can learn from the environment. Okay, so teacher may or may not be helpful. That will depend. Third scenario is passive learning from teacher annotated examples. Teacher annotated, teacher already proposes the examples. That is, for example, nature. This is a random process. So random instances will be generated, and that instance X is generated randomly. So teacher already provides the solution which is there. So it depends on the learner how he will gain. Okay, right? So these, how many training examples is sufficient? So it will depend on the scenario. For example, whether we are doing a training active learning, whether passive learning or passive learning from teacher annotated example. Okay, so next, so computational theory. So now we can brief that this computational learning theory, under this computation we have this several content. Okay, so on this we will study about the PAC learning framework, number 1. Okay, what is finite hypothesis space, number 2, and I will give you some examples of PAC learnable concept here. Okay, so today in this lecture I am going to discuss about these 3 topics which are very important. Okay. Secondly, there may be a question ki what is VC dimension and infinite. So when we used to consider finite hypothesis space, we will use this PAC learnable framework. How we can use this PAC learning using PAC? How we are going to use this PAC learning framework using for finite hypothesis space? And if my hypothesis space is infinite, then we will use another dimension that is called VC dimension. Okay. And third is mistake bound model. So these are the contents that comes under this computational learning theory, but in today's lecture I am going to focus on these 3. Okay. So while studying this computational learning theory, we have 2 important frameworks. Number 1, first framework is called as PAC framework, that is PAC. P stands for probably, A stands for approximately, and C stands for correct. Probably, approximately, correct learning framework, number 1. And second framework is called as mistake bound framework. This is number 1 and this is number 2. So we will focus on these 2 frameworks under this computational learning theory. Okay. And what happened is this PAC framework, it will identify the classes of the hypothesis that can and cannot be learned from a polynomial number of training examples. Okay, polynomial number of training examples that can be learned or not. So we are going to identify the classes of hypothesis using this PAC framework. Okay. So what we will do, we will just define a natural measure of the complexity for hypothesis space that allows bounding the number of training examples needed. So I am just going to illustrate it with the help of an example. Let's see. Okay. So PAC learning is probably, approximately, correct learning model. Okay. So for the sake of simplicity, I am just restricting my discussion to the case of learning only Boolean valued concept. Okay, we can also implement for real valued concept also, some non-Boolean valued concept also, but for the sake of simplicity, so that we can understand this concept, I am just concentrating the discussion using Boolean valued concept, that is from noise free training data. I am considering the data is noise free. Okay. So first of all, we have to do the problem setting. What is the problem setting? Matlab, what are the circumstances that we are going to provide to a system? Okay. So under this problem setting, we have lot of instances, lot of examples. So let us consider X is a set of all possible instances. Okay. X that will consist of all the possible instances, X1, X2, X3, Xn. Okay, instances, over which target function may be defined. Because we have already studied that how we are going to learn the system. First of all, we have to design the target function. After designing the target function, we will go for approximation, that we have already studied in unit 1. Okay. Now C is a set of target concept. We have considered, suppose C, a variable C is a set of target concept which will consist all the concepts to learn. Okay. So each target concept C in C is a subset of X. Okay. Each target function, each target concept C. So we have considered any concept which is we are going to implement for any set of target concept which is a set of X. X means number of instances that are coming from here. Okay. So each target concept C in C is a Boolean function. So for the simplicity, I have considered this Boolean function. So we can define this function like this. This concept such that X tends to 0 or 1. So this Cx is equal to 1 if X is positive example, yes or true. Okay. Otherwise, if that X is a negative example, then it will contain 0. So I have written here, define this function as Cx. Okay. This is a Boolean valued function. If it contains positive example, then we will assign 1, otherwise we will assign 0. Okay. Now next, the instances that are generated at random using some probability distribution. So we are generating the instances randomly. ठीक है. How it is generated? It is generated with some distribution that we call it a probability distribution, which is defined using this variable d. ठीक है. तो d may be any distribution. ठीक है. Instances are coming randomly. Okay. D is generally not known to the learner. Learner do not know how the instances are generated. Okay. D is required to be stationary. So these are the requirement. Stationary means that this distribution which does not change with time. Okay. So my training example X are drawn randomly according to this distribution. So training example is drawn randomly from this distribution and presented with target value Cx to the learner. Okay. So we assume the C is a concept and we have defined it as a target function, and it is how this target function is defined on the basis of some distribution that we have defined here with this variable D, probability distribution. ठीक है. तो number one we have seen this concept target function instances. ठीक है. Then we have done the distribution. Okay. And now third is hypothesis. Now let learner L considers set of hypotheses. ठीक है. That is represented by capital H. So after observing a sequence of training examples of the target concept, this is a target concept, then learner must output some hypothesis. है ना. And what is the output that is given by learner? That is defined by small h. है ना. From where it is come? It comes from the hypothesis space H, which is its estimate of C according to the concept C. Okay. So we have done the problem setting. Number one, instances using this target function which is defined by some target concept. Okay. Number two, distribution. So we have assumed that randomly instances are generated randomly with some function that we called it probability distribution D. Thirdly, we have defined this hypothesis space and we have considered that it will output some hypothesis H from capital H. ठीक है. So for example, how this I am just showing you an example, some classification example. For example, I am taking the three classes. Number one, first class is malicious, M, boring, B, funny, F. Okay. And I have three features. The first feature AI, second is A2, A3, A4. I have considered these four attributes. For example, first feature is representing the GUI present. Either GUI is present or not, graphical user interface, yes or no. This is an example that I am trying to show you. Second is deletes file, yes or no. If it is positive, then it will contain yes. If it is negative, then it will contain no. Allocates memory, yes or no. Creates new thread, yes or no. Okay. So for this example, we have to find out what is the distribution and what is the hypothesis. So for that, for example, we have number of instances. Okay. We have number of instances. These are the four attributes, and these are the values. For this example one, the first attribute A1 is yes, second is no, no, yes, and I have keep it in class B. Okay. B is boring. Okay. GUI is present, yes. Deletes file, no. If GUI is present and I am not going to delete this file, no. Allocates memory, no. Create new thread, yes. It is boring. Okay. So this is the classification problem. So several examples are given. So this is the one type of example. So firstly, what we have to do, we have to just find out the instances, number one. Then second, distribution, how it is distributed, that instances were distributed. And number third is hypothesis, whether that example, according to that example, that hypothesis H belongs to my capital H or not, my hypothesis space or not. On the basis of that, I will classify the class. Okay. So now here comes the concept of true error. So how this true error comes, this is also important. This true error is defined. This already we have defined. This true error already we have discussed in unit number 2. True error, है ना. So this true error, which is denoted by this error D of H of hypothesis H with respect to target concept C. So we have this hypothesis H, we have this concept C, and this probability distribution. ठीक है, it is defined, this true error is defined as a probability, PR. This is the probability, defined as a probability that H will misclassify an instance. H will misclassify an instance drawn at random according to D. So this is defined. This CX is a concept. So this is inequality. It means if this error will be defined as a probability of misclassify an instance drawn at random according to D. So we are randomly drawing an instance from our hypothesis H, है ना, from this capital H. So this equation can be represented using diagram also. So here you can see this instance. This is instance space. It is representing the instance space. This oval is C. This is H. So where C and H disagree, no instance is present here. ठीक है? And if C and H is agree, it will consist positive example C plus plus. है ना? So this diagram is showing an error of H with respect to C. Okay. Okay, so this is the definition and the concept. This concept C and H are depicted by the sets of instances without X that they label as positive. Okay, the error and this error of H with respect to C in the problem that a randomly drawn instances will fall into region where H and C disagree, है ना? So informally, how can I say that? Informally, this true error of H is just the error rate. Informally, this is defined as an error rate. Informally, if I say that, what is true error? This true error is an error rate. So we expect when applying H, we are going to apply H to future instances. We are going to apply H for future instances drawn according to the probability distribution D. So it is defined as an error rate informally, which we have defined as a true error using this equation. Okay. So there is a probability of coming this error. Always there is a probability of coming this error because we are going to just implement on the future instances, na? So we do not know what are the future instances coming out from the hypothesis. So there is a true error always. Okay. Now the key points that we have to keep in mind here is that it is always defined over entire instance space. True error is always defined over entire, not specific, on full entire instance space, not just the training data. Okay, number one. Second point is to keep in mind this error depends strongly on the unknown probability distribution D. Okay, and the error of H with respect to C is not directly observable to the learner. Learner do not know what error is going to come out. So and learner also do not know what concept is going to be implemented. Okay, so the error of H with respect to C is not directly observable to the learner L, and that can only observe performance with respect to training data. Learner L will just only going to watch the performance. Okay. Now the question is that how probable is it that the observed training error for H gives a misleading estimate of the true error? There may arise a question, na? How probably we are observing this training error for H, है ना? Because it can give a misleading estimate also of the true error, right? So there is a question. Okay, so for this question to be answered, we have to know about what is PEC learnability. Okay, probably, approximately correct learnability. The goal is to categorize classes of target concept that can be reliably learned from a reasonable number of random drawn training examples using a reasonable amount of computation, है ना? Secondly, unreasonable to expect perfect learning where error, that true error is equal to 0. So we can give a reason that true error comes out to be 0. So this need to provide training examples corresponding to every possible instances. So we need training example. So with the random sample of training example, there is always a non-zero probability that the training example will be misleading. Non-zero probability means this training example can mislead us also. So it will depend how many training examples we are going to take, correspond to every possible instance. Okay. So this will weaken the demand on learner. So hypothesis error may come. So what we will do? We will just do the approximation. Okay. There may be an error on training data, probably. Now I think you can find out why we have given the name this PAC, probably approximately correct. ठीक है ना? तो hypothesis error means we will not require a zero error hypothesis. We just approximate it. है ना? Require that error is bounded by some constant. So we have defined a constant epsilon. This epsilon is some error parameter. Okay. On the basis of that, we just finding the hypothesis error. Okay. Now, secondly, error on training data. We will not require the learner succeed on every sequence of randomly drawn training example. It is not the possibility that learner will always successful on every example. So probably number of times, how many times the learner will success, this we will check. So require that its probability of failure is bounded by a constant delta. So there is another new term delta comes here, which will tell the probability of failure that can be made arbitrarily small. So what is the aim of that machine? What is the aim of that algorithm? To reduce this delta factor. So delta is it is defined as a confidence parameter. Okay. So we have here two types of error. One error is called as training error. Second error is called as a true error. Okay. And one more error, that is called as hypothesis error. So we will approximate this error and we will check whether my training data have some error or not. Okay na? And with some this confidence parameter delta. Okay. So what is PEC learning? So P stands for probably, A is approximately, C for correct learning. PEC learning, है ना? So we cannot learn exact concepts from limited data. This we have already known. So I can show you with the help of an example that, for example, we have the set of all the positive examples here. This is a figure of a zebra here, 4 images of the zebra, है ना? And we have a negative example that will have a figure of horse, 4 different figures of horse. So what learner will do? Learner will try to learn. So what is our positive example? Whenever my system will recognize zebra, then it will give yes, otherwise no, right? So I will just use a classifier which will define in which class we are going to do. So what is my class? Positive example is zebra. It is given to a classifier that is generated as a positive example, right? It will identify right. Okay. If I given horse, that classifier will give a negative output, है ना, which is wrong. Am I right? So we that cannot learn even approximate concepts from the pathological training sets. So this example also represent that the positive example consists of this figure of horse, है ना? Negative example consists of this figure. So on the basis of pathological training sets, so what learner will do? Learner will just provide the input to the classifier. Classifier gives the zebra, but it is not there in the positive example. Then what will happen? It will give negative, which is wrong. And if it is given this horse, then it is positive, है ना? Then again it is wrong, है ना? Because the figure is not matching. So we can say that we cannot learn even approximate concepts from pathological training sets. So for that we will use this PEC learning. Okay. So we will define this PEC learning as a formal computational model which want to shed light on the limits of what can be learned by a machine है ना. How we can learn? By analyzing the computational cost of learning algorithm. So this is probably approximately correct learning. Okay, so what we want to learn? We just want to learn a concept. The concept is what recognizing algorithm we are using. Learning means what type of learning we are trying to do here. So computational description of recognizing algorithm, starting from, we will provide examples. If the examples were incomplete, with incomplete specification, then it will give error, definitely. That is to determine, it means that to determine uniformly good approximation of an unknown function. If we want to approximate an unknown function from its value in some sample points, so we want to determine uniformity. We always keep in mind uniformity. So how we are going to determine? We have several methods here. We can use the interpolation method, we can use pattern matching, also we can use the concept of learning here. Okay, so what's new in this theory, this learning theory? Accuracy of results and running time for learning algorithms are explicitly quantified and related, so we can relate them. So here, by studying this pack learning, we can find results accurately and in more appropriate time. Okay. So we can define this pack learnability. It will refers to the probably approximately correct. It is desirable that true error to be 0. We have defined it before, true error, this true error to be 0. However, to be realistic, if we implement in real world, we weaken our demand in 2 ways. So this demand can be weak because it is not necessary always we are predicting the true error. There may be a inconsistency, there may be a confusion there. Okay, so what are the demands? 2 ways. Number 1 is that true error is to be bounded by a small number epsilon, that we have shown before. Okay, that approximation, hypothesis approximation, number 1. Secondly, learner is not required to success on every training sample. So learner has to understand that he cannot gain a success on every training example, and rather than its probability of failure is to be bounded by some constant delta. So you have to keep in mind these 2 weakened demands. Okay, number 1 is small number epsilon and number 2 is this constant delta. Okay, this I have explained you before also. Let me show you where I have explained you. Yeah, here. Okay, so we have shown several instances here. So this pack learnability will help us to find out the approximation of this hypothesis error C. This I want to say epsilon and this error delta. Okay, so this we have shown it is always not necessary. By giving these examples, we are always want this positive example. It may be the case we must be get a negative output also. Okay, like this on the basis of this pathological training sets. Okay, so now this pack learnabilities, we have to keep in mind these 2 factors, epsilon and this delta. Okay, so hence we come up with the idea of probability approximately correct. Okay, and this pack learning is the only reasonable expectations of a learner is that with high probability it learns a close approximation to the target concept. Okay, so we specified 2 small parameters here, epsilon and delta, and require that with probability at least 1 minus delta a system learn a concept with error at most epsilon. Okay, so we have defined a definition here of pack learning framework. It is defined as a class of concept C which is pack learnable using a hypothesis class H if there exists a learning algorithm L. Okay, and how this learning algorithm will exist? Such that for all the arbitrary small, those 2 parameters delta and epsilon for all concepts, and those concepts C belongs to C because we have defined it Cx is equal to 1. Okay, and for all distribution D over the input space, there is a 1 minus delta probability that the hypothesis H selected from space H by a learner is approximately correct. So this is the definition that you have to keep in mind. Keeping in mind those with the help of those two parameters delta and epsilon. ठीक है, so there is 1 minus delta probability that the hypothesis H selected from this space H by learner. Okay, so this is the definition. So the value of this epsilon must lie from 0 to, this epsilon will lie from 0 to 0.5. ठीक है, तो consider a concept class C defined over a set of instances X of length n and a learner L using hypothesis space H. So C is PEC learnable by learner using H if all C, that concept belongs to C, how their instances were distributed, probability distribution with this D over X and this epsilon such that the value will lie between this and this factor delta such that this delta will lie from 0 to 1 by 2. It is also from 0.5. Then learner L will probability at least 1 minus delta outputs a hypothesis H belongs to H such that my true error is less than or equal to epsilon in time that is polynomial in 1 upon epsilon, 1 upon delta n and size C, which can be polynomially defined. So for this we are defining this definition of PEC learnability. Okay, so what are the requirement? Just keep in mind, arbitrarily high probability of 1 minus delta output a hypothesis having arbitrary low error, ठीक है. S learning must be efficient, learners learning must be efficient. How it is efficient? If it grows polynomially. Learners learning will be efficient if it grows polynomially. How it is grows? It will depend on the strength of the output hypothesis 1 upon delta, 1 upon epsilon and the inherent complexity of the instance space n and concept class C, which will tell the size of the concept. Okay, so we can represent this PEC learning with the help of this diagram. So we have training samples, lot of training samples which are come with this set xi comma cxi, which can be defined for in the hypothesis space H, है ना, I is equal to 1 to n. ठीक है, this training example we will give to learning algorithm. This learning algorithm will provide this hypothesis H and our H will belong to this capital H and there are two control parameters, this error and this parameter delta and epsilon. Okay, so keep in mind this diagram. Okay, so let me skip this. So the sample complexity for finite hypothesis space. So the sample complexity, so we will start from a good class of learner. ठीक है, and how we will define the class of a learner? The class of a learner is consistent. How we can say it is consistent? If it contains the consistent hypothesis. Consistent means the valid hypothesis, which were defined as one that output a hypothesis which perfectly fits the training data. So that hypothesis which perfectly fits the training data is called as consistent hypothesis. ठीक है, and it will start from a good class of learner. That consistent hypothesis is defined as an output coming out from that hypothesis space. Okay, so for understanding this, we just recall the definition of version space, which is defined as VS version space H. This H belongs to H that correctly classify the all training examples in D. ठीक है, and the property is that every consistent learner outputs a hypothesis belonging to version space. Okay, so this is, we can define these equations according to, we have taken the Boolean literals here. Okay, so this is the formal definition that we can define on the basis of those parameters. This is PEC learnable formal definition. Okay, so keep in mind this formal definition and I just conclude this lecture. Okay, thank you very much.